Take the bass line out. Jiggle. Let it bump though.
For your lesson today, we're going to be finding the volume of three-dimensional shapes using calculus and definite integrals. Reviewing what you already know, you know formulas for actual volume of shapes from geometry. Those will work if it's a simple shape. Now, as you know, not everything in the real world is a simple shape. So before we get into the actual calculus, let's go ahead and illustrate what volume can look like and how we're going to apply calculus. If I have a cube, alright, here is our cube, and we know that we can find the volume of that three-dimensional shape very easily by multiplying length times width times height. That is something you already know. Now, in order to apply calculus, what we can do is add up a bunch of small volumes to get the total volume. So if I look at one part here, and we'll call that a cross section. So think of just taking your cube and chopping it. And a cross section, in this case, it is a square. That is one cross section, one tiny piece. Now, if I were to take all of the little cross sections, we can create an infinite amount of them. If I take every single one of the cross sections and add up that infinite amount of volume, add up every tiny cross section that there is, we'll have the total volume of the cube. So that is what we're going to do, and it's kind of like a limit that we're going to be applying. We will add up every single cross section, every tiny piece of volume to get the total volume. That idea of adding up the cross sections is exactly what this illustration is trying to tell you. If I take a look at one cross section of this crazy three-dimensional shape, it has a cross section that looks like this. And if I take that one cross section and add it together with all of the other cross sections, they're an infinite amount, we would have the total volume. And that's what this Riemann sum is saying here. We take the sum of the areas of the cross sections, so I'm adding the area, multiplied by the change in x, which we know is infinitely small, we will have the total volume of the solid. Applying our calculus that we have, we can see that the volume of a solid can be expressed as a definite integral, or a number. The volume of a solid can be written with the cross-section area. So we're going to be taking the sum of all of those cross-sections. From A to B, an upper and a lower limit of integration, and it's given by the definite integral v equals the definite integral from a to b of ax dx. Now that ax is very important. This, you should be circling, starring, and highlighting. That formula is the area formula for a cross-section. So we have to know what shape the cross-section is, and we also have to know the geometry, which is the formula for the area of a cross-section. And then we'll integrate that formula for the area of a cross-section, add every single tiny cross-section up from A to B to get our total volume. And you can see the steps here. Sketch the solid and a typical cross-section. Find the formula for the area of the cross-section. Find the limits of integration, upper and lower. And integrate AX to find the volume. That is basically using the fundamental theorem of calculus to find the actual volume. Let's go ahead and take a look at an example. Alright, a pyramid 3 meters high has congruent triangular sides and a square base that is 3 meters on each side. each cross section of the pyramid parallel to the base is a square. Find the volume of the pyramid. Okay, so we've taken a look at this pyramid and we're going to set it on a coordinate axis so that we can apply the math. Now, it starts at the origin. And we know that that pyramid is 3 meters high. This is the base of the pyramid. The x-axis kind of runs like an altitude straight down through the middle. Now, we need to decide what type of cross-sections we have. Now, if I look at a cross-section, they are squares, and it actually tells us in this case that the cross-section is a square. So, I know that my area formula for a cross-section is the square formula. What's the area of a square? We know it's side multiplied by side, or side squared. Now, in terms of our problem, you can see the way that we have the pyramid set on the x-axis, that the length of these squares is going to be exactly equal to that x value. For example, when x is 3, the side lengths of the cross-section are 3. When x is 1, the side lengths of our cross-section is 1. So I know the area formula is going to be our x multiplied by our x. That is the area of a cross-section, whatever our x value is. Now that simplifies, as you know, to be x squared. So we've already started the process to find the volume. It's going to be a definite integral. Our area formula is x squared. Don't forget the dx. The only other thing we need is the upper and lower limits of integration. Well, how many cross sections do we have? We have an infinite amount, but we start at x equals 0, and we know our pyramid is 3 meters high. So we're summing them up to the x value of 3. This definite integral is simple to find once we have it set up using the fundamental theorem of calculus. So, using that knowledge, we will apply. We know that the antiderivative of x squared is x cubed over 3. That is all evaluated from 0 to 3. Simple to find, plug it in. 3 cubed is 27 over 3 minus 0 cubed is 0 over 3 is 0. Our answer is 27 over 3, which you probably know is 9. Now that is a volume. Every time we talk about volume, you have to have units cubed. Now, we know that our units are meters. So if we're going to be talking about volume, it's going to be cubic meters, or meters cubed. That right there is our volume of the pyramid. For example 2, we're going to follow the same process. It's just a little bit different setup for the problem. We're still going to use the definite integral to find the volume. We're just given an equation that is rotated around an axis. Now it may take you some time to get used to looking at rotations around axes, but after a million examples, as you know we'll have, you'll be good to go. So, taking a look, it says the region between the graph of f of x is 2 plus x cosine x, and the x-axis over the interval -2 to 2. Now let's break this up here just a minute. It's revolved around the x-axis to generate a solid. Our equation f of x from -2 to 2 is this curve. Now what we're doing is taking this curve and rotating it around the x-axis. When you rotate that around the x-axis, we are going to be creating some sort of solid shape. It kind of looks like a vase. So this is our curve that we are rotating around the x-axis to create this solid. Now we can find the volume of that solid. This is where calculus comes in handy, because in geometry we didn't have a formula that would give us the volume of this crazy shape. But now that we have calculus and a function that describes this curve, we can find the volume. So, first, what we need to know is what shape is a cross-section. So when I look at this, you can see that a cross-section is going to have the shape of a circle. Now, I need a formula for the area of any cross-section on this interval, -2 to 2. That value, we know the x-axis runs right through the center. So you can kind of picture that as the x-axis. This distance here is what we need, because we know the area formula for a circle. Area is pi r squared. I need the radius. The radius of this vase, no matter where we are at on the x-axis, is going to be the function value of f of x. So we have a function value. This radius has a value of 2 plus x cosine x at whatever x value that is. If you look at a different x value, take a look at this one at -1. It is a smaller radius, but it's still the same value from this function with -1 plugged in. So our area formula for a cross-section is going to be pi r squared, where the radius is this function value. It will be pi. Our radius is the function itself, 2 plus x cosine x squared. Pi r squared. Pi r squared. Area formula for a cross-section. Now, all we need to do from there is set up our definite integral. So our volume is given by the definite integral. Lower and upper limits of integration we know are -2 to 2 of our function for the area for the cross-section, pi, 2 plus x cosine x squared. Don't forget the dx. Once we have this, the setup is complete. Now this one, the antiderivative of this is a little bit tricky. So I would imagine this one would be a calculator active question. So going ahead and doing this in the calculator, I'm assuming you can do that by now. You should come up with an answer of approximately 52.43. Now we don't have any units in this problem. They weren't given, so we'll just say it's units cubed. So 52.43 units cubed. That right there will be the volume of this crazy shape.